Welcome to the 9th lecture in Applied Math. The topics that we will explore in this lecture include elementary row operations and an algorithm to find the inverse of an invertible matrix. Okay, so we will begin this lecture with the exercises from the previous lecture. And in the first exercise, we need to show that any square matrix with a row of zeros is singular. So let A and B be any two square matrices of order n with row entries where the matrix A has a row of zeros. Then there exists an index I in the range from 1 to n such that the ith row vector of the matrix A is the 1 by n 0 row vector and so the ith row vector of the product A times B is the ith row vector of A times the matrix B, which is the 0 row vector, times the matrix B, which is the 0 row vector. And hence it is impossible that there exists a square matrix B of order n with real entries such that the product A times B is the same as B times A, which is the identity matrix, since the identity matrix does not have a row of zeros, and therefore the matrix A is singular. And in the second exercise, we have a matrix A, which is a 2 by 2 matrix with rows A, B, C, D, where the difference of products A times D minus B times C is not 0, and a matrix B, which is a scalar multiple, the scalar 1 over A times D minus B times C times the matrix with rows D negative B negative C A, and we need to show that the matrix B is the inverse of the matrix A. So first we compute the product A times B, and this is 1 over A times D minus B times C times the matrix A times the matrix with rows D negative B negative C A. And so we have 1 over A times D minus B times C times the matrix with columns A times D minus B times C, C times D plus, minus C times D, negative A times B plus A times B, and negative C plus B plus A times D, or A times D minus B times C. And so this is 1 over A times D minus B times C times the matrix with columns A times D minus B times C 0 and 0 A times D minus B times C, which is the 2 by 2 identity matrix. So next we compute the product B times A. So we have the matrix B times the matrix A And this is 1 over A times D minus B times C times the matrix with columns A times D minus B times C, negative C times A plus A times C, or negative A times C plus A times C, D times B minus B times D, or B times D minus B times D, and negative C times B plus A times D, or A times D minus B times C. So this is 1 over A times D minus B times C times the matrix with columns A times D minus B times C, 0, and 0 A times D minus B times C. And this is the 2 by 2 identity matrix. So since A times B is the same as B times A, which is the identity, the matrix B is the inverse of the matrix A. And in the third exercise, we need to show that the set of all square matrices of order n with real entries is a monoid, but is not a group under matrix multiplication. So proof: let A and B be any two square matrices of order n with real entries. Then the product A times B is once again a square matrix of order n with row entries, and so we have closure. Now let A, B, and C be 3 square matrices of order n with row entries. Then the product A times the quantity B times C is the same as the quantity A times B times the matrix C. Since for any 3 conformal matrices the product is associative, now there exists the n by n identity matrix in the set of square matrices of order n, such that for every matrix A in this set, we have that A times the identity is the same as the identity times A, which is the matrix A, and hence the set of all square matrices of order n with real entries is a monoid under matrix multiplication. Now notice that there is a 0 n by n matrix with real entries, and there does not exist a matrix B in the set of square matrices of order n with real entries, such that the product 0 times B is the same as B times 0, which is the identity, and hence the set of all square matrices of order n with real entries is not a group under matrix multiplication. Since it is not true that every element in the set of square matrices of order n with real entries has an inverse. Okay, so now we'll start with some new material and we'll begin with a definition. There are three elementary row operations. That can be performed on a matrix. The first is we can multiply one row by a non-zero constant The second is that we can interchange any two rows and third, we can add a non-zero scalar multiple of one row to another row, and these are the three row operations that we call elementary row operations. So notice that for every elementary row operation, there is an inverse operation and this inverse operation is also an elementary row operation. The inverse of multiplying row I by a non-zero constant which we'll call C is to multiply row I by the reciprocal of C. The inverse of interchanging row I and row J is to once again interchange row I and row J. And the inverse of adding a non-zero constant C times row I to row J is to add negative C times row I to row j. So let's look at some examples of elementary row operations and their inverses. So we'll start with a 3 by 3 matrix with rows 3, 4, 1, 2, -7, -1, 8, 1, 5. And we'll perform the elementary row operation of multiplying row 1 by the non-zero constant 3. Then row 1 is the row 3 times 3, which is 9, 3 times 4, which is 12, and 3 times 1, which is 3. Rows 2 and 3 are not changed, and so we have 2, -7, -1, 8, 1, 5. So next, we will perform the elementary row operation of multiplying the non-zero constant 1 over 3 times row 1. 1/3 of 9 is 3. 1/3 of 12 is 4. 1/3 of 3 is 1. Rows 2 and 3 are not changed, and so we have 2, -7, -1, 8, 1, 5. And so by performing an elementary row operation on a given matrix and then performing the inverse of that row operation, we once again obtain the original matrix. So let's start with the same matrix: 3, 4, 1, 2, -7, -1, 8, 1, 5. And let's interchange rows 1 and 3. Then row 1 is 8, 1, 5. Row 2 does not change, 2, -7, -1. And row 3 is 3, 4, 1. And if we once again interchange rows 1 and 3, then row 1 is 3, 4, 1. Row 2 does not change, 2, -7, -1. And row 3 is 8, 1, 5. And so by performing the interchange of two rows and following that with the interchange of the same two rows, we once again obtain the original matrix. So again, we start with the matrix 4, 3, 4, 1, 2, -7, -1, 8, 1, 5. And we will perform the elementary row operation of adding -2 times row 1 to row 3. So rows 1 and 2 do not change. Now row 3 is -6 plus 8, which is 2, -8 plus 1, which is -7, and -2 plus 5, which is 3. And now we will apply the elementary row operation 2 times row 1 and add that to row 3. So once again, rows 1 and 2 do not change, and so we have 3, 4, 1, 2, -7, -1. And row 3 is 6 plus 2, which is 8. 8 minus 7, which is 1. And 2 plus 3, which is 5. And so by applying the elementary row operation, -2 times row 1 plus row 3, and then following by the inverse of that row operation, 2 times r sub 1, or row 1, plus row 3, we obtain the original matrix.